for the conjecture. The second part is for some symmetry breaking for the solutions via machine text for ground state solution. The first part is we consider the following Henon-Lane-Emden elliptic systems. Laplace U equal x a v p, Laplace v equal x b u q, where the dimension is n greater than 2, greater or equal than 2, p q greater than 0, a b in R, and C system is a natural extension of weighted Lane-Emden equation minus Laplace U equal x a u p, x in Rn. Also, we consider this system. And first, we consider this Lane-Emden equation. Let us introduce some Hardy Sobolev equivalent PSA equal n plus 2 plus 2a over n plus 2 if n greater than or equal to 3. If n equal to is infinity. When a equal to 0, PS 0 is Sobolev equivalent with denoted by PS. And data struck CPAM 1981 show for the single equation, if A equals 0 and P less than PS, then equation 2 has no positive classical solutions. And this is a very famous result. Later, when Xiong Chen and Tongming Li in this paper, Duke Math Journal 1991, gave a new proof for the above theorem by Kelvin translation and main plan methods. As the case, A not equal 0 is more difficult and increasing. Especially for A less than or equal to minus 2, the one single equation, this one, has no positive solution. U in C2 minus 0 and capital CR, and in this case there's no such kind of solutions. And so the interesting thing is for A greater than minus 2. In this paper, Han and Soffit, PDE 2012, conjectured that let n greater or equal than 2, A greater than minus 2, then equation 2 has no positive solution if P greater than 0, less than PSA. And in this paper, they proved when n greater than 3 equal to 3, they show the conjecture 1 for the this conjecture is true for bounded positive solution. In fact, say if they assume that the positive solution are bounded, so they have proved this. And later, in 2017, Songming Guo and his student in Science Math China Mathematics gave a positive answer for this conjecture. And furthermore, Li, my previous student, and myself, we consider the more general equation for the single equation, div and x set gradient u equal x l u p, x in Rn. And for this kind of equation, you can see this paper and Yi Hongdu and Professor Zhong Mingguo, say CVPDE 2015. They share some background about this equation. We consider the solutions of this kind C2 Rn minus 0, and Ux is bounded near 0, and we consider C2 in this region, and C is bounded in near 0. And we define n prime equal n plus theta greater than 2, and tau and is L minus theta greater than minus 2. And PS theta L equal this one, prime n prime minus 2, and this part is n prime plus 2 plus 2 tau. This is tau. If tau, if is theta is 0, so it's only this part. If this is a 0, so it's n minus 2, and this part n plus 2. So this is generalized n plus 2 over n minus 2. We have the necessary and sufficient condition for the existence of positive solutions of this equation. So our result is about this equation. And the method is we studied the equation of this equation and use the Monotone theorem for this positive solution, and then get the Lewis type theorem. And the result is this one. Let theta L in R n greater or equal to 3, n prime equal n plus theta greater than 2. Then equation 3 have positive solution in M if and only if tau equal L minus theta greater than minus 2 and P greater or equal to PS theta L. And let theta equal 0 and less than L greater than 0 in equal 3, then our result, by our result, the conjecture A1 is true for n greater or equal to 3. Also can prove this conjecture, this equation, or mentioned above. This equation has no positive solution if L greater than minus 2 and P less than PS theta L and greater than 0. So our result also can prove this conjecture for n greater or equal to 3. And now we return to the Henon-Lane-Emden conjecture for system 1. System 1 is we return to this. We consider this this system, and then we define the critical Sobolev hyperbola is n plus a over p plus 1 plus n plus b over q plus 1 equal n minus 2. And we call the pair PQ subcritical if the pair PQ lies below the critical Sobolev hyperbola is set PQ satisfies this inequality. This is greater than n minus 2. So it's under this line, under this line. If PQ not equal 0, not equal 1, we define alpha. This number is 2 times P plus 1 plus A and PB is over PQ minus 1. And beta equal 2Q plus 1 plus B plus QA over PQ minus 1. Now, if PQ is not equal 1 and UV is a solution of 1, then R alpha U Rx, R beta V Rx, and this is also a solution of 1 for any R greater than 0. We introduce this scaling invariant, which is important in our proof. So this invariant scaling invariant is important in our proof. If UV is a solution, this also is a solution 2 for any R greater than 0. And we also consider this kind of solution, AB for AB through R, BQ greater than 0, since AB may be negative. So classic solution 1 will be considered in this class, C2 Rn minus 0, and CRn, also in CRn. So equation, so we also consider this kind of solution, U greater than 0, V also greater than 0. For this conjecture support in this paper, Goshop and Fasley and 2014, support PQ is subcritical, is under the line, at the line, at that curve. And the system 1 has no positive classical solution. So see, in that paper, you can see this conjecture. And in fact, they give some partial result about this conjecture. They assumed the bounded positive solutions. If the positive solutions are bounded, they can prove this conjecture. Also, for this kind of solution, this kind of conclusions, and Professor Vernon and Gigakomini, ADE 2010 system shows that the system has positive radial solutions if and only if this pair was above or on the critical Sobolev hyperbola. So this they obtained that the bar conjecture is true for radial positive solutions. So if you are assume or you can prove the positive solutions are radial, so you can prove this conjecture. So in fact, so if you know the radiality, so you can prove this conjecture. Now, in fact, we don't know whether all the positive solutions are radial. When A equal B equals 0, conjecture A2 is known as Lang-Emden conjecture for the following system: Laplace U equal VP, Laplace V equal UQ. And in fact, this curve is PQ equal 1, and there's a curve PQ 1 over P plus 1 plus 1 over Q plus 1 equal 1 minus N2 over N. So this curve. So also for Lang-Emden conjecture, Martidier, DIE 1996 shows that the system 6 has no positive solutions if and only if PQ was subcritical. They had proved under this line, there's no positive radial solutions. This implies Lang-Emden conjecture is true for positive radial solutions. So if the positive solutions are, if all positive solutions are radial, so the conjecture is proved. And about Lamb conjecture, there are some results. For n less than or equal to, the conjecture is a consequent or relative easy result. And can see these two papers for this, and they have proved such the systems, in fact, the system inequalities. They can admit no control solutions for max alpha and beta greater or equal to n minus 2. And so not only solutions, only for the inequality is they can get some no result, no solutions. For n greater or equal to 3 and Henon-Lane-Emden also differential and integral equation 1996 show this conjecture hold if PQ less than or equal to 1 or PQ greater than 1 and the max alpha beta greater or equal to n plus 2. So they proved for the Lamb conjecture, they have proved if PQ in this area, PQ less than 1, the conjecture is true. And above this PQ equal 1, the curve, and this curve, there are some regions they have proved. For some regions they have proved, but also some regions we don't know. And Plastic, Quintner, and Soufflet in this paper, Math Journal, 2007. In this paper, they established the W lemma and show that if PQ greater than 1, then non-existent or bounded positive classical solution for system 6 implied not non-existent positive classical solution. And this, you can clear? You see the W lemma, they proved this conjecture for dimension n equals 3. And later, himself, Soufflet, Advanced Math, 2009, proved this conjecture for n equal 4. This is for Lamb conjecture. For A equal B equal 0. Now, the Lamb conjecture is still open for n or equal greater than or equal to 5. So there are some there are some regions in this part. In this part, there are some regions we don't know the non-existent for n greater than 5 or equal to 5. So this conjecture is still open. Now we return to Henon-Lane-Emden conjecture. Now this conjecture is less than 2 and then understood and assumed tangent to prove it. For bounded or positive solutions, this paper they have proved the conjecture for R3. They assumed, in fact, they assumed all the positive solutions are bounded. So they under their assumption, they proved this conjecture. Now we complete this conjecture for R3. The result is this support n equals 3, AB in R and PQ greater than 0. If minimum AB less than or equal to -2 is or this case minus AB greater than minus 2 and PQ is subcritical. Then system 1 has no positive classical solution. This is our main result about Henon-Lane-Emden conjecture. Now we introduce the simply for the proof. This in fact, so we made some estimate first by the sphere average of the solution and get some lemmas which get the estimate of solution at infinity. On the basis estimate, we can show if this or PQ less than or equal to 1 or maximum alpha beta greater than 6, then system 1 has no positive classical super solution. So for this case, even there is no positive classical super solutions. Now we only need to consider the case alpha A, B, A and B greater than minus 2 and PQ, P times PQ greater than 1. So we only consider this case left. So this part we have through some lemmas to prove, and this we use the problem of embedding on L2 and energy estimate and another lemma, so we can get this inequality. Now we by scaling invariant of the solution, we use our scaling invariant and this integral on BR, and then we get this estimate. Now the supernet 4 is this one is for the subcritical, and this one implies alpha plus beta greater than n minus 2. See, alpha plus 1 plus beta greater than this one. So this is less than 0. So we can know let R go to plus infinity. So we know U and V are equivalent to 0. So this proves this theorem. Now we can also consider the single solutions for the Hans-Sofler conjecture we mentioned above. We can U equal V and A equal B and Q equal P, P equal Q, and this also can prove also our result implied A1 is true for R3. So this we get such result. Now we consider the further study on Henon-Lane-Emden conjecture. We consider the following higher order Henon-Lane type irreversible Laplace M1, Laplace M2, XA VP and XB UQ, and this to M1 less n, to M2 less n, and PQ greater than 0, and AB greater than minus 2. For this for play harmonic system, and we can support this is subcritical. Now it becomes this n minus 2m for m1 equal m2. For this case, we can get some result. And then system 7 has no positive solutions. This we give this conjecture. For M1 equal M2, this case, the conjecture this system has no positive solution either. For all M equal 1, AB equal 0, we have mentioned above. And for M equal 1, and also we have mentioned above. Also, when if M1 equal M2 equal M, and 2M less than N, and AB equals 0, and Jiaquan Liu, JDE 2006, they show this conjecture hold for P greater than 1 and less than N plus 2M over N minus 2M. Also this for Q, and PQ not equal 1 and 1, 1, this point, and also this. And if M1 equal M2 greater than 1, PQ greater than or equal to 1, and AB greater to 0 or equal to 0, then firstly, and show this conjecture hold for bounded solutions when N equal to M plus 1, or for bounded radial solutions. So some if we assume the solutions, positive solutions are bounded or radial, it can easily to prove something. Also, in this paper, Arthur Yan, CPAA 2016, show that this conjecture hold for solutions which satisfy a certain decay. Now we know when P in 0, 1, this solution, play harmonic, UP has no someone hasn't should turn off your phone, or even some. The equation, this equation has a positive classical solution in Rn, and system with AB and MR M equal 2 and P equal Q in this one has a positive classical solution when studying someone maybe turn off your phone, please.有些噪音总是。When studying this, 有人没关静音，有人需要静音啊。We assume P this one. We only assume PQ greater than 1 for simplicity. Our main result is this. Suppose that AB greater than minus 2, 2M less than IN, P less than 1, greater than 1, and less than or equal to P0. Also for Q, and same, and P0 is this N plus 2M plus 2A and over N minus 2M. All this, and Q is also similar. Then system 7 had no positive solutions. So for the play harmonic system, also we can prove some result. For proof this, we should first know some regularity of the positive solutions as the origin. Also, we study the equivalence between higher order Henon-Lane-Emden elliptic system and some properties integral systems. Here, using the method of main plan for the integral system, and we prove the result for the integral system. Then we get the result, the non-existent result of the differential equation. So the first theorem is for proof this main theorem. We first prove this theorem. Suppose PQ greater than 0, minimum AB greater than -2, and M1, M2, N in capital N with this. In fact, this theorem is true for M not equal M1 can be they cannot be equal. They certainly is true for M1 equal M2. So this is more general. If this is a positive classical solution of 7, then U is C2 M1 minus 2 and V C2 M2 minus 1. So the solution is has some regular even in the orange, even in 0. And the second theorem is suppose PQ equal 1, AB greater than -2, M1, M2, N is in capital N with this one. If UV is a positive classical group of 7, then UV is a solution of integral system. This is UX equals C1, this is VP, and over X minus 1, N minus 2 M1. And this is V, and this is UQ. So this effect, they are equivalent for the integral system and the differential system. So we use the to prove this non-existent of this system is enough. So this is so we that is the equivalence between the Henon-Lane elliptic and some property integral system. Then use the method of moving plan for integral system and decay existence and positive and energy type inequality. We can obtain the main theorem. Main theorem of this system. Also, we can consider the single solutions as this one. This is current. For further study on Henon-Lane conjecture, we can also consider the more general systems. This is some singularity here in this part, and we have X theta. This system, and this also this is extension, natural extension of this Lambda equation. Now we also some PDES theta A. This Hardy-Sobolev exponent for this kind of equation. Also, we consider the solutions of this kind and UV greater than 0. For system 11, for this system, we also can define the critical soluble hyperbola like this: n+2 over p+1, n+b over q +1 equal n prime minus 2. This n prime and this n prime is n plus theta, and call the pair PQ subcritical if the pair PQ lies below the critical soluble of hyperbola is this inequality. And if this PQ not equal 1, and we can also similar to 5, and we define alpha now is this one, and beta is here is theta. There's theta, also theta. There's theta. Also, we have some invariance like this. If UV is the solution 11, and also this also is solution. Now, if theta is not 0, when all for the subcritical case system has no positive solution is 0, an open problem. Now, we conjecture as this, suppose this n prime against this one, and the minimum alpha against minus theta, b minus theta greater than minus 2, and PQ is subcritical system 11 has no positive classical solution. Here is the main method is the sphere average, Passayev type identity, soluble inequality, and RSN +1 feedback, and the measure argument and the scale invariant of the solution. We obtained the Liver type theorem for the general Henon-Lane-Emden sigma in R1. And we show if the pair of exponent is subcritical, then the system have no positive solution for n equal 2. And for n equals 3, we only prove that has no bounded positive solutions. So there's the so if we add assumption all positive solutions are bounded, we can get this conjecture for n equals 3. But for n equals 2, we can prove this. The result is equal n equal to theta greater than or equal to 0, theta greater than 2. The pair is subcritical then 11.7 has no positive classical solution. And for n equals 3, theta can extend the change. The region theta is can be negative to -1, and this greater than this, and the pair is subcritical and has no bounded classical solution. For n equal 2, here no growth or decay conditions are imposed on solutions. But for n equals 3, due to the method we adopted, we need to consider the bounded solution. So since the method is some limited, so maybe I think it's true. So this part is part A. For the part B is for the symmetry breaking via Morse index. We also consider the Henon equation, general Henon equation, Laplace A minus mu u, Laplace u mu u, and x alpha x u p minus 2 u, u equals 0 on the boundary. And the corresponding problem for the Schrodinger Henon system is this kind plus u, Laplace u plus u1 u and x alpha, and this partial u fu and fuv partial v fuv x alpha, and this kind of system. Here omega and n R is set to Rn is the unit ball. Here, omega is the unit ball. And n greater than C, 2. And this is positive. Mu 1, mu 1, mu 2 is positive. And P greater than 2. Alpha greater than -1. F satisfies the following assumption. F is of class 2 on R2, homogeneous of degree P greater 2, and satisfied FUV greater than 0 for UV in R2 -0. In special case, when where FUV is equal A1 U4 and HR plus A2 V4 over 4 plus B U square V square over 2 with content A1, A2 greater to 0, B greater to or equal to 0. System 16 is a weighted version of the nonlinear Schrodinger equation of this one. This one is usually we have studied more than 20 years, recent 20 years. There are many mathematicians who studied this, such as Ambrosidi, Dancer, Bash, Zhitao Zhang, Juncheng Wei, although myself also do some research on both Einstein and Einstein concentration Schrodinger system. And so this 16 is the general one, is a general weighted version of this one. And 15 is merely called Henon equation when mu equal 0. 0 is if there is no cis part, is called the Henon equation and introduced by Henon and in 1973 and in ultraphysics. And the first mathematician paper, Living Ni, who observed the presence of the weighted term leads to new critical equivalent n plus 2 alpha over n minus 2 for non-existent of critical positive solutions. After Ni's work, 15 have been studied in recent years. William, CVPDE 2003, CCM 2002 studied the existence of ground state of 15 and their asymptotic behavior, both for alpha greater 0 fixed, P go to 2 star, and P in this range, alpha go to infinity. In fact, his 2 star is 2n over n minus 2, and this one. Also, they studied the partial symmetry and symmetry breaking result for ground state solution of Henon equation in Smith, William, CVPDE, and the partial symmetry result for sign changing, also from Bash, West, William, this paper, and shifting and William JEMS 2008. Note that if 17 is considered with delicate boundary condition, then every solution UV is positive, then they are radial by Torres symmetry result based on moving prime methods. And the same radial result applied to more general system 16 in the case when alpha equals 0. The system is positive, it satisfies this condition. So in alpha equals 0, you can prove the UV positive solution are radial, even for 16. But on the other hand, the moving prime methods break down in the case alpha greater than 0 and simply breaking of ground state is impacted. Now, the notion ground state is defined in the case P greater than 2 and less than 2 star. Both 15 and 16 have a variation structure, and the solutions are the critical point of the critical function of this one for single solution and this one for the system. And this is the XR FUV and this part. And I have a few minutes, and the corresponding linear manifold are given by this one and also this one for the system. And after the remark about is expected for alpha greater than 0 large ground state of 15 and or respective 16 are not radiosymmetric. And when mu equals 0, and in fact, this has been proved in this paper. Usually, there are two approaches to prove symmetry breaking. The non-radiosymmetric ground state of 15 or 16 for R large. First one is a direct energy comparison between radio and non-radio function in the linear manifold. You compute the energy of the radio and non-radio functions. If the non-radio functions, the energy of non-radio functions is less than the radio part, radio case, so you can prove the ground state is non-radio. The second approach is use the Mercy index, which is equal to 1 for every millimeter of H on NH or every millimeter HS on NHS. And this approach is in fact much more general and can be defined for any P greater than 2. And the Mercy index are not only for ground state, but also for critical point associated with more general minimax principle. Now for define Mercy index, we use a linear operator as you for single solution, and for systems, linear for the linear operator of this, and we consider the number of negative eigenvalues. The main result is this general law, my previous student, and Weiss and myself, and the P greater than 2, we have this is mu H, this mu H alpha is if A is radio non-trivial radio solution of 15, and this is Mercy index, and this is infimum of all the Mercy index. This we define this one, this one, UH, this one, and this one is this is choose H. So this is some measure. So this is go to infinity as alpha go to infinity. Also, this UH alpha for the system, this also go to infinity and alpha go to infinity. So use this theorem and we can prove there is alpha bar greater than 0 such that alpha greater than alpha bar. Every ground state of 15 is non-radio symmetry. And also every ground state through 16 is non-radio symmetric. Okay, that's all. Thank you for your attention. Thank you very much.